that's as funny as my set's going to get. Right. So, when you start your PhD, one of the first things... Can people actually hear me? Am I really...
A bit too close.
Yeah, too close. A bit distorted. That's a new one. Nobody's told me on that before. Right. Is that better? I don't know if I've got quieter. Right. Good. Okay. So the first thing people often say to you is they say, "Oh, what faculty are you in?" Because they want to know what you do. I don't seem to have any microphone now, so I might put it down. I'm not really sure. That's better. Right. So they say, "What faculty are you in?" And I have to say, well, I'm in the School of Social and Human Sciences. And so the great thing about that is, they then say, well, naturally, are you a social scientist or are you a human scientist? I'm a mathematician, I'm not either of those things. Luckily, they changed this. So they decided, no, mathematics, we will not hide it in the corner anymore. Well, we will, physically, we'll put it in the corner of the campus, but what we're going to do is we're going to add you on the end. So now we're the social, human, and mathematical sciences. Genuinely, we are the sham sciences. Acronyms. And generally, when you say you're a mathematician, I need the mic back, do I? Okay. I'm going to be distorted again. So, genuinely, when you further away, I have... That looks quite dodgy, if I'm honest. Anyway, so yeah, genuinely they then say, oh, you do maths. Well, great. They haven't said I've distorted before, but they say, so do you do like really big sums? Then they say, oh, I've got a shopping list here. Can you add it up for me? No, I don't do that. So I do something called group theory, and naturally, being in the School of Social and Human Sciences, you'd think that would be about movements of groups of people. Well, no, it's not. So what I do is group theory, which is the study of symmetry. Not cemeteries, symmetry, okay? So I look at the symmetries of objects. Yeah, that was quite a desperate joke. Right, so group theory. So we're not groupie theorists. Because if we were groupie theorists, we'd be people that follow rock stars. And then you can have a groupie. And then you can have a groupie theorist. So for the maths people, I genuinely thought this up today, you then have an example of the free semi-group on two generators. But for the non-maths people, which are much... You can tell you're the majority because there weren't many laughs to the laugh. If you then take a group, you can then take a group theorist, and you can take a group theorist, and you can keep on going, and then you have a cube. Right. Okay. So this shows that I can't draw, and that something's going on with my flip chart. Right. Technical error. So, on this we have quite clearly some cups and some tea saucers. You can tell that. Right, so, I said I can't draw. I was going to ask somebody, but we were running low on time, but I was a bit nervous about going up to somebody and asking them if they could draw some saucers for me. So these are the abstract representation of cups and saucers. There you go. Right, so now you can draw them if you like. So, you might ask, are there the same number of cups and saucers? And then you'd look at me like I'm mad, because that's not a big sum, that's not even a small sum, that's an easy question. So you count how many cups there are and you count how many saucers. And as long as I've drawn it correctly, have I done 5 of each? Yeah, good, okay. You count 5 and you count 5. I think I can do that, because that's what I did on there. And then you say, well, there's the same number of cups and saucers. And now you're still thinking, yes, this is a comedy set, but this guy's a bit funny. So, in 1845, Cantor, who was a mathematician, wanted to generalise this idea to infinity. So he wanted to say, look, people before him were sort of like, well, infinite things, they're the same. But he wanted to do it a bit more rigorously. So his idea, I'm sorry, I'm going to show you some maths in a second, but I apologise in advance. Right, so he said, infinite things, the way we're going to do this is we're going to count differently. So what we're going to do is, rather than say, I'm counting this lot, what he's going to do is he says, there's the same number of things if for every one of these I can associate one of the other things. So he wouldn't count these cups and saucers, he would just put each cup with one saucer, which is quite a natural thing to do, and you can see why I've tried to draw cups and saucers now. Right, so I now have This is something you can't do with a PowerPoint. This is going to get progressively more difficult, isn't it? Right, I've only got one more, maybe two more things to do. Right, okay, so quickly. Right, so infinite things. So here we've got infinite things. 1, 2, 3, 4, blah, blah, blah. Right? I skipped over some of them, but you imagine there's infinite things. Right. And so I'm going to do something strange though. I'm going to say, imagine your thesis was like this, it's this many infinite number of chapters. If I had to write a 0th chapter, surely that's more chapters than somebody who hasn't written a 0th chapter. But I'm going to show you now they're the same. It's like magic, see? Magic. Right, so what I'm going to do is the person who wrote the 0th chapter, I'm going to match that up. You can see that's a 0, even though I'm using a highlighter. So 1 associates with this one, then I'm going to do 1 associating with this 2, this like this. There you go. I've paired up these two things. Don't worry, it'll get more interesting in a second. Right, so the other one. Now what about all the even numbers? So you split your thesis up into 2 parts, all the even chapters, all the odd chapters, and you asked 2 different people to write it. Surely you've halved the amount of work they've got to do. So surely these infinities can't be the same. If you think about all the even numbers, surely they can't be equal to all of the normal numbers. But there's a way of associating them. So with 1 I'm going to associate 2, to 2 I'm going to associate 4, 3 I'm going to associate 6, and 4 I'm going to associate 8, and so on. There we go. So all the even numbers, with Cantor's definition, there's the same number of those as there are normal numbers. Right, so now we're going to prove everyone wrong on saying that there's only one kind of infinity. So we're going to find another one. So Cantor, a little bit of a reveal there, maybe it's going to fall down. He looked at all the numbers between 0 and 1, and he said that's a different infinity to all the numbers 1, blah, 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 blah. Okay, so now we're going to do this. Don't worry, nearly to the end. It's not as many slides as it looks. Can I just put this down? Technical errors. He's a real page turner. Right. Right, okay, so now what do we do? So I decided I'm going to use taxi company numbers for all the numbers I'm going to use. And the reason was that I was thinking, well, you might all feel a bit tired at this point because you've had a lot of maths. And so I thought taxi companies, they'll give you a lift. Right, puns, they're wonderful. Right, so I've nearly finished. So what he did was, he first of all assumed you could write all the numbers between 0 and 1 and match them up with a list. So this is a number, match up with 1, this is another number, match up with 2, and so on. He assumed you could do that. And then he's going to show that that's impossible. So he assumes you can do this, and then around all the ones on the diagonal, this is why it's called Cantor's diagonal argument, he's going to put a box. So each number that's in a box, if it's between 0 and 8, I'm going to change it to add 1 to it. And if it's 9, I'm going to go back to 0. Okay? I'm only lying to you a little bit. So, all the numbers down the diagonal. Right, so the first one, I'm going to replace that with 9, because I'm going to add 1 to it. This one, 1, this one, 7, this one, 2, this one, 6. And you can keep on going. So we've got a whole list of numbers here, and I'm claiming that all of them, you hit all the numbers that are between 0 and 1. Every single number. There is now a big problem. This number that I've just made is not on this list. Now let me justify why. So it can't be the first number, because the first digit, it doesn't match up. It can't be the second number, because the second digit won't match up. And if you keep on going, it can't be any of the numbers on the list, because this digit will be different. So I've just made one number that wasn't on my list. So there's no way, whenever you do that, whenever you say, I've written a list that gives you all the numbers between 0 and 1, you can't have done that, because you can always create one number that wasn't on your list. So there's no matching between these two. So these numbers here, there's more of them than the numbers here. Right, I'll end with something funny. Here's the names of 3 more mathematicians. Right, so I've been recently typing some things, and you type it on a bit of maths. I don't need a page turner, thank you, Nick. Right, so I've been typing it on a bit of math software, and I thought I'd run a spell check, because that's a sensible thing to do when you type things wrong. And it came up with some spelling suggestions, and I thought they were quite funny. So these are all mathematicians, and it decided that they were wrong. It decided that even though it's a maths piece of software, these people can't exist. So Osin, who's a mathematician I featured quite a few times, said, I don't know who Osin is. Who's Osin? But I do know that Norse god, Odin. Do you want Odin in your thesis all the way through? Hickman's embedding theorem. Wouldn't it be funnier if it was Hangman's embedding theorem? And finally, I did group theories. It's not surprising it's got group on the end, but Grigorchuk group. Are you sure you mean that? Sure you don't mean your church growing group?